Welcome back. This video lesson is going to be regarding fluid friction. Alright, now last year you may recall me saying we're always going to avoid air resistance or wind resistance because it makes the math significantly harder. And that was a partial truth. Right? The math is not significantly more difficult. It's just another algebra. Right? The problem is the number of situations that actually apply to it is what gets tricky. Now, basically, anytime that we're talking about fluid friction, we're going to be talking about a term that is called drag. Drag is a capital letter D. Right now, some of you might remember from last year a couple of times we talked about density. We said density wasn't a capital D. It was going to be this Greek symbol rho, which kind of looks like a lowercase p with no top to it. Okay? They actually had, they had developed the terminology so that these things would still be able to fit in the same situation. Right? Because the density of the material, or the density of the fluid, is going to determine how much friction is going to be caused. Because think about it. If you were to try to drive your car through air, it would be different than trying to drive your car through water. And driving through water would be different than trying to drive through maple syrup. Because the density of the fluid is different in each situation, that needs to be factored into the equation. All right? Now, just like the coefficient of static friction, there is going to be a drag coefficient. The capital letter C is known as our drag coefficient. And simply, the drag coefficient just tells you how this material will pass through the other material. Just like the different coefficients of static friction had to do with the different surfaces that were involved, the drag coefficient is going to have to do with the two surfaces that are, the surface that is flowing through the fluid. Sometimes materials will flow easier through, sometimes they will flow more hard through it. Right now, the other things that are important here, A, which is surface area. Now this is of the solid. The surface area of the solid. All right? Think about it in terms of aerodynamics in vehicles. All right? The front end of a Lamborghini has much less surface area than the front end of a Mack truck. The main reason is the performance of one versus the other. You would expect a Mack truck to be able to haul a lot of material, but not be able to haul at a specifically high speed, whereas you would want a Lamborghini to just go really, really fast. At least that's why you would spend so many hundreds of thousands of dollars on it. And the other thing that's important here is the velocity. All right? Basically the speed of material. Okay? This is pretty much all that goes into it. All this stuff here is going to factor into drag. The equation for drag. The drag is going to equal 1/2 the coefficient of drag, rho, or the density of the material, A, surface area, V squared. Okay? Now, what that's telling you here, and what you should be able to notice, is the biggest factor in this equation, the thing that is going to change the most about the drag in general, is going to be the overall speed of the material. The higher the speed, the more drag you're going to have. All right? So the more speed you have, the more drag you're going to have. Now, yes, the surface area, the coefficients, the density, that's all going to impact it. But this is going to impact it at a much greater rate. As you increase the velocity, that is going to greatly increase the drag. Okay? Now, in essence, we can also figure out what's going on and to try to determine what the terminal velocity of an object is based upon this equation. Okay, last year we talked about terminal velocity. Right? Terminal velocity is basically the fastest that an object can go. Right? it is the absolute top speed, right? Now, that top speed is completely determined upon the surface area, the coefficient of friction, the density of the material, and it actually has to do with the weight of the material as well. Okay, now, really neat thing here. If anybody has watched that free fall from space or from the upper stratosphere or whatever it was, the Red Bull thing the other day, the reason he was able to reach a much higher terminal velocity than other skydivers is he was jumping through an area which had a much smaller rho value. The density of air in the upper atmosphere is so low that you're able to reach a much higher speed than you would in the lower atmosphere. Okay? But think about what ends up happening here. If it's at its terminal velocity means it's the absolute fastest. So that means that the acceleration in that case has to equal 0. Well, then how does that work? It's obviously going to have weight acting on it, the force due to gravity. It is obviously going to have drag acting upon it. So the force due to gravity minus the drag has to equal 0. So in this case here, when we reach terminal velocity, that means that the weight of the object has to equal the drag force. Now, if you were to do that, you can actually determine exactly what the speed limit is, what the terminal velocity is for any object falling through any media. So we're going to go back to the same equation that we had here. Drag equals 1/2 c rho a v squared. And force due to gravity is just mass times acceleration due to gravity. I'm just going to leave it as this. But if drag equals force due to gravity, then at terminal velocity, that's going to equal the force due to gravity. So I want to try to figure out what the velocity is of any object based upon this situation. So what I'm going to do is I'm going to multiply both sides by 2. I'm going to act like this part doesn't exist. Multiply both sides by 2. Multiply both sides by 2. And divide both sides by c rho a. C rho a. So v squared, the terminal velocity squared, equals 2 times the object's weight divided by c rho a, square root both sides, and you end up with the terminal velocity equals the square root of 2 times its weight divided by the coefficient of drag times the density of the material times the area, the cross-sectional area of the material that it is going through. Okay? Now, I will do a basic problem with this. Right? I'm going to leave a little bit more trouble for you guys to try to work on your own, but I'm going to start the practice video or practice problem on the next video. So I'll leave this one at this, and let's work on to the next.